The first one is going to be the steel wool. In this one, steel is a combination of, it's an alloy between carbon and iron. It's an alloy between carbon and iron. And it is really very, very fine threads, right? So you have very, very fine threads. Have you ever seen a steel wool? Okay. Well, so you'll see it in a minute. It's really, really fine threads. And what we're going to do is we're going to put a 9-volt battery. And we are going to go from, the electricity goes from the negative side to the positive side, right? So the electrons are going to try to go from one side to the other. But if I have a 9-volt battery, the electrons cannot go from one side to the other automatically because they don't have a path. And the electrons need a path to go from one side to the other side of the battery, right? So if I put my finger, do you think electrons will go? Very, very few, but they do. And we do have a little gadget that I can show you that very, very few do, but very, very few, but they do. But if I put like a metal, they'll immediately go because metals are good conductors, right? So they'll immediately flow, and actually the metal will get hot, and that's called a short circuit. So basically that's what I'm gonna do. I'm gonna put a metal, which is the steel wool, but this metal is really thin, like thinner than hair, and it's gonna put a whole bunch of resistance, right? So as the electrons are trying to go really fast, because of the resistance, they start heating up. And when the steel wool gets heated up, it creates a fire. And now the fire self-sustains the rest of the steel wool, and the whole thing goes on fire, right? And what this does is it creates a redox reaction in which we don't really care about the carbon, we care about the iron part of it, which is the one that actually corrodes when we have anything made of iron. This ring right here that you see in the ring stand, you see that it's all corroded? That's likely carbon steel. And it is not the carbon, it is the iron that is corroding away. It's getting oxidized or reduced, Harrison? Oxidized. So what we're gonna do here is we are going to have that. The more we fluff it up, the more contact it's gonna have with oxygen in the air. And then we're gonna make rust, right? And then you're gonna have some questions. You're going to get a piece of steel wool. You are gonna weigh it. Everybody's gonna get a piece of steel wool. Before you all get up, I'm gonna give you your piece of steel wool. Then somebody in your group is gonna weigh it. We want every single significant figure that the scale gives you. Every single one of them, because they're all important. Then you're gonna do this experiment with the 9-volt battery, and after that you're gonna weigh it again. And then you're gonna tell me why it gained or lost mass. So you're gonna have to try to tell me, I want you to think about it. Why do you think it would have gained or lost mass? And that's basically that little tiny, little mini micro lab, right? It's actually pretty cool. That's the funnest thing we'll do today. The next one has to do with aluminum and hydrochloric acid. This is our standard. We've been putting, what else? What other metal did we dissolve with an acid? No, we didn't. We couldn't dissolve copper. Zinc. We dissolved zinc with an acid. We couldn't dissolve copper because hydrochloric acid was not high enough to dissolve it, right? But we did do zinc. Well, this one is similar, right? The aluminum is more reactive than the hydrogen. The aluminum, and I'm still seeing people ask this question, will not displace the chlorine. The positives displace the positives, the negatives displace the negatives, right? So you don't go and displace somebody, you know, if you give and you take, you don't displace, a giver won't displace a taker, they'll join, right? So please don't do that. Don't have the aluminum displace the chlorine, that will never ever happen. So the aluminum will displace that, and then we'll have our products. Now, because I want you to focus on redox reactions and balancing with redox, I'm not gonna give you this equation. I want you to use the aluminum solid still. That's what we have. I'm gonna give you a piece of aluminum solid, actually 3 pieces. You are gonna put it in an acid, We're going to call it H+, right? In an acid. And this is going to give you, what's going to happen? The aluminum is going to give the electrons to the hydrogen, right? So as it gives the electrons, how many electrons will the aluminum get rid of? 3, because it has 3 valence electrons, right? So on the third column. So it's got 3 valence electrons, so it'll get rid of 3. And then we're going to end up with aluminum 3+. In solution, you're dissolving the metal. You will not see anything when you're done. It will be clear. Plus, what else are you gonna have there? What do you think we're making this time again? And the same thing that we did with the penny battery. Hydrogen gas. You make hydrogen gas. Because the hydrogens, each hydrogen is gonna grab an electron, then they immediately join because it's a diatomic molecule, and then they escape, right? So I want you to do, you are not gonna do it right now, but I want you to do the oxidation and reduction, or you can do it now if you think you have the time, or do while you're doing the lab. The oxidation and reduction have reactions. I want you to add them up, and we're gonna balance that equation using redox. So you're gonna balance that equation using redox.
Is oxidizing getting more positive?
Yes, like most metals, when you think of oxidizing, I mean, there's oil rig and Lewis Gear and all that, but I like to think of, hey, metals normally get oxidized. The one that I like to think about is iron getting oxidized. What does oxygen normally do? It oxidizes things. Normally in a combustion reaction, oxygen is oxidizing, right? In many things, oxygen usually oxidizes, therefore the name. Is there a time where oxygen can be reduced? Yes. Thus, so there may be an exception. You cannot just get cocky and go, hey, oxygen is always oxidized, right? Oxygen is always reduced. Oxygen is an oxidizing agent, but it in itself gets reduced. Now the metal gets oxidized.
Whenever you're writing the half reactions for oxidation, whenever you do plus blank electrons,
Yeah.
for oxidation, is it on the product side?
So what I like to do so that I don't get confused, especially when you're learning, what I decided to do a long time ago was I will always write my oxidation reaction first. So I will see which one is getting more positive, and that will be first, and reduction will always be second. So the one that is oxidation, I'll put my electrons on the right side, and the reduction will be put on the left always. So I wouldn't have to think about it. But when you lose, you always lose towards your products, which makes sense now in class, but when you're on the test, you're like, heck, I don't know where to put the electrons, right? So I always put the oxidation first and the reduction second, so that I know it's always right first and then left for the next one, right? Because you gain in the reduction. Now in this lab, you're gonna have 3 samples. You're gonna get 3 test tubes that we may need to wash because the previous class didn't wash them, and they had to wash the ones from the previous class because they didn't wash them. So whatever you leave, I'll make sure that block 3 cleans, or maybe we'll just clean it so we can start brand new next week. So you're gonna put a little tiny piece of aluminum. How big? Little tiny. We don't want to waste a lot of aluminum or a lot of acid or any of that. So maybe a square centimeter. You know, a centimeter is about the end of my pinky. Little tiny piece. You are going to scratch 2 of these ones. One is gonna have 6 molar hydrochloric acid, and the other one is gonna have 0.1 molar hydrochloric acid. Right? Now the last one, you are not gonna scratch it, and you're gonna put 6 molar hydrochloric acid in it. How much? Just enough to, you don't even have to cover it, because as it starts dissolving, it's going to go down, kind of like when you make pasta. The pasta can be above the water and then eventually it all goes down. So you don't even have to cover it. You just need to put enough, maybe 2 milliliters. but you'll see once you put it, you don't have to cover it. What do you think you are gonna see with the 6 molar and the 0.1 molar?
I think more aluminum is going to dissolve in 6 months.
So this happens very fast, right? That's what we expect to see. We expect to see this one to happen very slow. Why? Because there are only very few hydrogens in there, and they have to be in contact with the aluminum, right? And they have to have enough energy, and the reaction has to happen. There are so few, right? The other one is loaded. So if he wants to give electrons, this one's loaded, right? So he can give them easily. This one is not. Why don't I want you to scratch that one? What does the scratching do? It exposes the aluminum, because aluminum is a reactive metal, so you will have naturally a coating in it, right? And you don't scratch it and then go do things and come back, although it may be okay, it's not that reactive, but you scratch it and then you put it and you put the stuff. You're ready to do your thing. What do you need to do here? Draw a particle diagram. I just want you to see that a concentrated reaction has got more hydrogens. You can also put more chlorines, but we're not really caring about the chlorines. It's got a lot more hydrogens, and this one should have just a few hydrogens, right? So you have 2 particle diagrams so that you can explain to me using the particle diagrams what happened. For the carbon snake demo, I'm gonna do it. I was going to let you all do a little bit, but it's really, I'm using 12 molar sulfuric acid. It's not the nicest thing in town. So I'm gonna have sugar in a small beaker. Again, I don't wanna use too much. And then I am going to, and sugar is made out of carbon, hydrogen, and oxygen. You don't care about the ratio, but it is made out of carbon, hydrogen, and oxygen. It is a covalent thing, but now we are going to put, again, an acid. I'm gonna color it differently. I'm gonna put 12 molar sulfuric acid. I use 6 molar with block 3 because I forgot. I haven't done this in a while. And the 6 molar may have worked by now. But it did. It worked by now, but it took forever. Actually, the class was over and they were never able to see it happen, right? So 12 molar is what we really need to use because we need the higher concentration for it to happen. What happens, and I think I talked about this earlier, what happens with sugar and sulfuric acid? What is sulfuric acid? It loves water, right? It dehydrates things. It has a huge affinity for water, right? Huge affinity for water. So if you have something like carbon, hydrogen, and oxygen, you don't really have water in there, but this sulfuric acid will grab these two and make water evaporated as water, right? So what we're going to do is the sulfuric acid, and then you're gonna have this, which is the coolest thing in town. So we have 2 that we made in the 2 classes. That one was broken, but it starts with about this much sugar, and then I put the sulfuric acid of, right? And then look what happens. And that is so what? If we got rid of the H's and the O's, what were we left with? Carbon. What? You had lots of moles of carbon. I always think of chemistry as magic. I mean, I know it's not magic and I understand it a little bit, but it really puzzles me how something like sugar can eventually do this. Something like toilet paper turns black. Again, it doesn't grow like this, but you're left with carbon. What happens in here is that kind of like when you whisk an egg, did we talk about this last time, whisking an egg? Same thing, these gases are going to make pockets in here, and they're going to literally whisk and fluff because it's so hot. This you cannot touch. I think it reaches 700 degrees C, which is crazy hot. But I don't